Hello everyone, welcome back to our course on abstract algebra. Today we're going to be talking about subgroups. So what are subgroups? We have already seen a number of them. A subgroup is a group within a group. So for example, we have the complex numbers under addition, the complex numbers under addition, say, and we have inside the complex numbers, we have the real numbers, we have the rational numbers, we have the integers, and each of these under addition is a group itself, so that is a subgroup. So let me actually write a formal definition of this. Let G star be a group, and let H star be another group, such that, well, one, H is contained in G, and two, the binary operation is the same. H and G share the same binary operation. G and H share the same star, and what that actually means, remember that in principle, we have a star goes from G cross G to G, and then we can restrict to H cross H, and that would in principle land in G, but we want that landing in H. So that's what it means, is that they have the same binary operation. Okay, and then if so, then H star is called a subgroup of G star. Typically, we say that H is a subgroup of G, but it is important to emphasize that the star, the binary operation, has to be the exact same thing. Okay, so for example, let me again go back to this example of the complex numbers. So we have the complex numbers and we have, say, the integers. Then under addition, we have the integers under addition is a subgroup because addition is closed for the integers, and it is the same addition that we use in the complex numbers. Now, if I go to the natural numbers under addition, they are closed under addition, but this is not a group, so this is not a subgroup. Okay. Another example is the following, that I can have Z under addition, and then I can embed in here, I can take 0, 1, which is a subset of the integers, under addition modulo 2. Okay, so in here we are thinking of 0 and 1 really as Z modulo 2. So I'm going to be adding 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, and so on. So this is a group. This is a group, but this is not a subgroup of Z plus, because they do not share the same operation. The binary operation is not shared. It's not the same binary operation. If it was the same, we would have that in here, 1 plus 1 is 0, but it isn't. So this is a containment of sets, but it is not a containment of groups. So it's not a subgroup. Okay, before I go on and give more examples of subgroups, I also want to show a couple of results of how to identify subgroups. So let H be a subset of G, and with G G itself a group, and let G star be a group. Then H star is a subgroup if and only if 1, E is in H, 2, if G and H are in H, then G star H is in H, so H is closed under multiplication, under the star, under the binary operation. And if H is in H, then H inverse is in H. So H is also closed under inverses. And the proof of this, so consider H star, first of all, by 2, H is closed under star. So that means that star is a binary operation on H itself. Then I need to check associativity on H follows from associativity on G, because H is a subset of G. So if it was associative on elements of G, then it is associative on elements of H. So for all A, B, and C in H, we do have that A star, B star, C is the same as A star, B star, C, because A, B, C are in G, and G is a group. So star needs to be associative on G. What about G2? Is there a neutral element? Yes, there is an element E in H by the first assumption in this theorem. And E star H is H star E is H for all H in H, again because H is in G and G is a group, and therefore E is the neutral element. Here when I say E is in H is where E is the neutral element of G. And last, again, for inverses, for all H in H, there is an H inverse which is in H by 3, by my third hypothesis, and such that H star H inverse is H inverse star H is identity because, again, H is contained in G and G is a group. So to prove that something is a subgroup, we actually just need to make sure that the identity is in the subset, that the subset is closed under the binary operation, and that the subset is closed under inverses. In fact, you can accelerate this a tiny bit, and you can prove that let G be a group, and let H be contained in G. Then H star is a subgroup if and only if one, H is non-empty, so there is something in it, and two, if G and H are in H, then GH inverse is in H. And why is that? The reason is that, well, let's prove it. It is an if and only if. So let's go in this direction first. So suppose that H is a subgroup. Then we know, first of all, that E is in H. So H is non-empty, and that proves one. And second, if G and H is in H, then first of all, H inverse is in H because H is a subgroup, and G star H inverse is in H because it is closed. So we know in this case we are assuming it is a subgroup, and we know it's closed under star, so those are satisfied. So this proves 1 and 2. So now let's go in the other direction. So let's assume that H is non-empty and it's closed in this sort of weird way that G times H inverse is in H. So first of all, since H is non-empty, I'm assuming conditions 1 and 2, we have something in H, and by 2, G times G inverse is in H. I'm taking H also to be G, but G times G inverse, that is the identity. So the identity has to be in H. And let's prove that it is closed under multiplication. So now, well, by 2 also, actually, I'm going to prove that it is closed under inverses. So since now we know that E is in H and let's say G is in H, then by 2, E times G inverse must be in H, but G inverse times E is just G inverse, so G inverse is in H. So, so this tells me that E is in H. This tells me that H is closed under inverses. And finally, multiplication. We have, so if I have G and H in H, I do have that by what I just proved, H inverse is in H, and thus by property 2, we have that G star H inverse inverse, which we showed that H inverse inverse is H, has to also be in H. Therefore, H is closed under multiplication or under star, and therefore I can use the theorem by our previous theorem. H star is a subgroup. Which is what I wanted to prove. So we can actually just use this criterion to show that something is a subgroup. So let me show you some examples of subgroups now that we know that. So for example, in the complex numbers under multiplication, the non-zero complex numbers, so this is the complex numbers except 0, under multiplication, this is a group, it's an abelian group. And inside of it, I have just plus or minus 1 under addition, under multiplication. This is a subgroup. How do we prove that? 1, the identity is in plus minus 1. So plus minus 1 is non-empty because in particular we do have the identity in there. And then every time I have G and H in plus minus 1, then how much is G star H inverse? Well, this is going to be, I don't know, plus or minus 1 times, and then the inverses is going to be something like some minus or plus 1. This product is always going to be a plus or minus 1, which is going to belong to plus or minus 1. So by our corollary, by this corollary, we have checked that the subset is not empty, and that we have this property, and therefore, since it shares exactly the same, we share the same star, the same binary operation, then it is a subgroup. So it is a subgroup. Okay. Also, we also have inside. Let me change color. Inside the complex numbers, the non-zero complex numbers, for a fixed n, we have what we call the roots of unity, the nth roots of unity. What are the roots of unity? The roots of unity are elements, zeta. The nth roots of unity are those elements whose nth power gives you 1. Okay, so mu n is going to be, well, those complex numbers whose nth power is 1. If you use sort of like the polar form or the exponential form of complex numbers, then you will see that it has to be that they are all of the form e to the 2 pi I a divided by n for some a from 0 up to n. Okay, so this is a subset of complex numbers, and let's see that they are actually a subgroup. So first of all, so I'm going to try to show that the nth roots of unity under multiplication are a subgroup of the complex numbers, the non-zero complex numbers under multiplication. This is a subgroup. So let's prove it. Let's see, first of all, so again, let me copy down here that mu n is all those complex numbers e2 pi I a divided by n for a between 0 and n. So 1, mu n is non-empty. We have, for example, 1 is in mu n. 1 is precisely e to the 2 pi I to the 0. When I put 0 in there, I get a e to the 0, which is 1. Okay, so there is something in there. And 2, first of all, what is the multiplicative inverse? So if I have e to the 2 pi I a n, what is the multiplicative inverse of this number? It will be, well, it is precisely that will be minus 2 pi I a divided by n. And is that another number of this form? Is that another number of this form? Well, yes, it is precisely e to the 2 pi I n minus a divided by n. Why? Because I can actually, so remember that e to the 2 pi I is precisely 1. So I can write this one as 1 times e to the minus 2 pi I a divided by n, and then write this as e to the 2 pi I times e to the minus 2 pi I a divided by n, and then this is e to the 2 pi I n divided by n times e to the minus 2 pi I a divided by n, which is e to the 2 pi I n minus a divided by n. So that's what the multiplicative inverse is. And this is also one of my elements in my set. So that is the inverse. And now let's multiply two of them together and see that they are also another root of unity. So now if I have, so G and H nth roots of unity, then G will be some e to the 2 pi I a divided by n. H will be some e 2 pi I b divided by n. And then how much is G star H inverse? That is e to the 2 pi I a divided by n times e to the 2 pi I n minus b divided by n. And this will be e to the 2 pi I, well, it will be a plus n minus b divided by n. And that number, notice, by the way, that the exponent in the roots of unity, this exponent is just class modulo n. So this will be, if, say, if a plus n minus b is congruent to c modulo n, then this is e to the 2 pi I c divided by n, which is another nth root of unity. So we have the multiplication of the roots of unity is the multiplication in the complex numbers, and we have shown that the set is not empty and that the set is multiplicative, in that we have that any G times any H inverse is also an element of the set, and therefore the roots of unity under multiplication form a subgroup of the non-zero complex numbers under multiplication. Okay. Let's see other examples of subgroups. One subgroup that is just, well, it's a subgroup, is that I always have, if I have a G, if I have a group, G star, a group, then I know that there is an element in G, namely the identity element, and therefore I can create a subgroup which is just the trivial subgroup, is a subgroup called the trivial subgroup. And notice that the identity, the set with just the identity, is non-empty, and any product within it is in it. The inverse, the multiplicative inverse of E is E itself. So E times E inverse is E, which is in this set. So this is another subgroup. Similarly, also, well, G star is a subgroup of G star. So the total is a subgroup. We never assumed that H was strictly contained in G. So G itself is a subgroup. All right. Those are just silly subgroups. But let me show you some other subgroups that are not so silly. Remember that we had GL2, for example, over the reals under matrix multiplication. So this is matrix multiplication, and these are 2 by 2 matrices with real coefficients. and such that AD minus BC is non-zero. Those are 2x2 matrices with non-zero determinant. Then there is a subgroup of this, which is called SL2R under matrix multiplication. And now this is going to be 2x2 matrices. Again, A, B, C, and D real numbers. And the determinant is going to be exactly 1. Okay. Why is this a subgroup? This is a subgroup because the determinant of a product of matrices is the product of the determinants. That's a property of matrices and determinants. And therefore, if A and B are in SL2, then their determinants are 1, and the determinant of AB will be the determinant of A times the determinant of B, which will be 1 times 1 equals 1. And moreover, it is closed under inverses because the determinant of A times its inverse, well, on one hand, it will be the determinant of A times its inverse is the identity. The determinant of the identity is 1, and the determinant of this will be the determinant of A times the determinant of A inverse. And therefore, if this is 1 and the product is 1, that implies that the determinant of the inverse also has to be 1. And that implies that the inverses are also in SL2. So SL2 is closed under multiplication, it's closed under inverses, and the identity element under multiplication, which is the identity matrix, is of determinant 1, so it is also in the same subset. So this is a subgroup. Let me do one last example related to something we did in a previous video. Remember that in a previous video, we actually compared and realized Z modulo 4 under addition and Z modulo 2 direct product with Z modulo 2 under addition. We realized they are different groups because their Cayley tables, the tables of addition, are different. And they have different properties. Here we're going to do the same. We're going to show that these two groups are different by looking at their subgroups. So there is something called the lattice of subgroups. We can actually list, in this case, what are all the possible subgroups. And in this case, there is 0. The trivial subgroup is a subgroup. And now, what other subgroups are there? If I have 1, the element 1 in my subgroup, then 1 plus 1 is 2, plus 1 is 3, plus 1 is 0. Therefore, I would have the entire group. So I also have the entire subgroup, which is just everything. That's a subgroup. And, okay, so if I have 3, the same thing happens. If the element 3 is in the subgroup, 3 plus 3 is 6, which is 2. And 2 plus 3 is 5, which is 1, and every element is in there. What happens if I have 2, the element 2, then I have 2, but 2 plus 2 is 0, so there is one more subgroup, which is the subgroup with just the element 0 and 2 under addition. So these are all the possible subgroups. Now, what are the possible subgroups in here? Well, by the way, let me actually draw this in terms of what, as I said, a lattice. I have Z modulo 4Z. Then I have the subgroup with just 0 and 2, and then a subgroup which is just the trivial subgroup. So these are all the subgroups of Z modulo 4. Now, in this case, in Z modulo 2 cross Z modulo 2, I'm going to have, let me actually draw it again as a lattice directly. So I have Z modulo 2 cross Z modulo 2. I have the subgroup which is just the trivial subgroup, like that. Then I can have, for example, I can have the element 1, 0. So if I have 0, 0, and 1, 0, 1, 0 plus itself is 2, 0, which is 0, 0. So actually, this is closed under addition. Then there is the subgroup that has the element 0, 1, that similarly is closed under addition. And then there is the subgroup that has the element 1, 1. As soon as I have any other element, in addition to one of those, then I get my entire group. So the lattice here looks like this. So that's none of those is contained in each other. These ones are not contained in each other. Their intersection is this one, and then the only subgroup or that is on top of those is the entire group. But now you see that this and this are not the same, so there are different subgroups. There's the number of subgroups is different, for example, and therefore these two groups cannot be the same group. They cannot be isomorphic. We will get there. Isomorphic will be, we'll say that, is there some reordering of the elements? Is there some map, some bijection that respects addition that tells me these two are exactly the same group? And because the number of subgroups is different, we actually know they must be different groups, essentially different. So this is one of the techniques we'll use to try to differentiate subgroups. We're going to try to classify subgroups, we're going to try to classify groups, finite groups under isomorphism, and this will be one of the tools we will use to do that. So next time we will talk about a particular type of group, which is called cyclic groups.